In this videocast, we'll look at one new way of finding enthalpy of a reaction. Thus far in this chapter, we've looked at three different ways of finding delta H, or enthalpy, heat at constant pressure for a reaction. First one was by looking at a thermochemical equation, where we said for every 2 moles of A and 1 mole of B, 1 mole of C produced, negative 100 kilojoules is given off. Secondly, we looked at constant pressure calorimetry. A calorimeter is something that has a reactional curve that we measure the change in temperature, and we use the equation Q, or heat of a reaction, is equal to M times the specific heat capacity. M is mass, C is specific heat capacity, times its change in temperature. The third way was using a bomb calorimeter, which is another type of calorimeter where Q is equal to the negative heat capacity of the calorimeter times the change in temperature. And the last way that we've looked at thus far in this chapter was using Hess's law, where we took and manipulated equations and added them together by multiplying or dividing the equations by a value to get the goal equation that we wanted. And we did a number of example problems and homework problems like that. The last method of finding enthalpy in this chapter that we're going to look at is by using something called enthalpies of formation. And the enthalpies of formation, if you would please for a moment, take out your textbook, are talked about on page 191, and if you'd follow along with your textbook or on the page right in front of you on the screen, we're going to take an in-depth look at how enthalpies of formation can help us find the enthalpy of a reaction or enthalpy of a change that's going on. By methods that we discussed using Hess's law, we can calculate the enthalpy changes for a great many reactions tabulated from enthalpy values. Many experimental data are tabulated according to the type of process. For example, there are extensive tables that exist of enthalpies of vaporization, enthalpy for converting liquids to gases, enthalpies of fusion, enthalpy for melting solids. That's what fusion is going from a solid to a liquid. Enthalpies of combustion, which would be an enthalpy or a delta H for burning a substance in oxygen, and so forth. A particularly important process used for tabulating thermochemical data is the formation of a compound from its constituent elements. The enthalpy change associated with this process is called the enthalpy of formation, or sometimes known as the heat of formation, and it's labeled delta H with a little f down below it, where the subscript F indicates that the substance has been formed from its component elements. The magnitude of any enthalpy change depends on the conditions of temperature, pressure, and state, whether it's a gas, liquid, or solid crystalline form of the reactants or products. In order to compare the enthalpies of different reactions, we must define a set of conditions called standard state conditions, at which most enthalpies are tabulated. The standard state of a substance in its pure form at atmospheric pressure, 1 atmosphere, as we'll learn more in chapter 10 about, and the temperature of interest, which we will choose to be 298 Kelvin or 25 degrees Celsius. This is known as the standard enthalpy change of a reaction, and it happens at 1 atmosphere or 20 and at 25 degrees Celsius. This is defined as the enthalpy change when all reactants and products are in their standard states. We denote a standard enthalpy change as delta H with a little circle or degree sign up above it, where the superscript degree sign or little circle indicates that it's at standard state conditions. These things that we just read are super duper important to have memorized in your brain, that enthalpy formation is delta H with a small f. It's formed from its constituent elements. That the little circle right here means at standard conditions, 25 degrees Celsius and 1 atmosphere of pressure. The standard enthalpy of formation for a compound is the change in enthalpy for its reaction forms 1 mole. Notice it says 1 mole, that's another key, of the compound from its elements, with all substances in their standard states. We usually report it as its delta H circle F value. It's enthalpy of formation at standard conditions value. Notice what the little symbols mean. F means formation, little circle means standard conditions, the triangle means change, and H means enthalpy. If an element exists in more than one form under standard conditions, the most stable form of the element is usually used for the formation reaction. and then they give an example right here. Let's jump into a couple of examples for you, but before we do that, take a look at the top of the page here on page 192, and notice they have a table 5.3, that lists a number of standard enthalpies of formation at 298, and they list a whole bunch of things alphabetically right here. And there's actually a larger table in the back of your textbook in Appendix C that lists tons of thermodynamic quantities for selected substances. In Appendix C, you can see it's listed alphabetically, and they have the enthalpies of formation at standard conditions for a lot of things here, and it goes on for actually 3 pages worth of this. And you should get used to looking back in Appendix C in the 1100s or so of your textbook to find these enthalpies of formation. So take a moment right now and find your practice exercises and put those out in front of you. Pause the video now if you need to, and make sure that you have these questions in front of you that start with "give it some thought." And make sure that you have a pencil or a pen in front of you so you can take some notes and write down the answers to these questions as we go along, and do some sample exercises with standard enthalpies of formations. Pause the video now if you need to get these things out. In Table 5.3 on page 192, the table we just looked at, the standard enthalpy of formation of C2H2 is listed at 226 kilojoules per mole. Write the thermochemical equation associated with delta HF for this substance. Well, remember, it's the standard enthalpy of formation, which means it's formed from its constituent elements. We know it's going to make C2H2. That's going to be my product. But it's going to be formed from its elements. So it's going to have to come from hydrogen. But what is the standard form of hydrogen at 1 atmosphere and 25 degrees Celsius? Well, it's H2, and it happens to be in a gaseous form. So you have to indicate that it's diatomic and that it's in its gaseous form. What's the standard form of carbon at 25 degrees Celsius? Well, it happens to be graphite. And if you're not familiar with that, that's the simplest or most stable form, also the cheapest form of carbon at those standard conditions. And since I need to write it for 1 mole of this product, because remember the standard enthalpy of formation has to be for the formation of 1 mole of this, I'd have to put a 2 right here in front of this. This would be the equation, the thermochemical equation associated with the enthalpy of the substance when I add the delta H at the end is equal to 226.7 kilojoules per mole. And usually you don't have to put the per mole here because it's given that it's 1 mole of this stuff being formed. But this is the thermochemical equation for the formation of acetylene, C2H2. Let's take a look at sample exercise 5.10. For which of the following reactions would the enthalpy change represent a standard enthalpy of formation? For those which is not, what changes would need to be made to make the reaction in the correct standard conditions? Well, if you look at the first reaction right here, notice it forms Na2O solid. That means it has to form from the constituent oxygen at standard conditions. And look at that, it does. Oxygen, O2, notice it's diatomic, and it's gaseous at 25 degrees Celsius in 1 atmosphere. And Na, which is a solid at standard atmospheric pressure. And if you're not sure what these are at and you want to look something up, look at Appendix C. Look at Appendix C, because Appendix C. If you're not sure that sodium is a solid at room temperature at 25 degrees Celsius, well, you might not know that, but take a look at it in Appendix C to find out. Another good place is on a periodic table that's a little bit better than one of these, because they'll give you what the standard states are, whether they're solid, liquids, or gases. As a matter of fact, I'm not sure that I have one here, but you have a colorful one, I think, that shows you what's a liquid and what's a solid. And there really are only 2 things that are liquids at room temperature, and that's bromine and mercury. Those are the only 2 that are liquids. Everything else is either solid or gas at the temperature. So this one would be a standard enthalpy of formation equation. How about this one? Okay, this one shows KCl solid forming, and it comes from Cl2 gas, which is correct. because chlorine is a gas at 25 degrees Celsius in 1 atmosphere, but it says that potassium is a liquid. Potassium is not a liquid at room temperature, and so no, that rules it out. And also, remember that the standard enthalpy formation should form 1 mole. 1 mole of the product. Does it form 1 mole of the thing of interest? No, it forms 2. So it would have to be written as one of these guys right here, which would force me to put a 1/2 right here and a 1 right here, and I'd have to put potassium solid right here to change it to be the standard enthalpy formation equation. Okay, and then lastly, letter C. If you look at this reaction, it doesn't form one substance from its elements. It's actually the reverse of it, because it's taking a substance and breaking it up. Now, if you reverse this equation around, you could get close to the standard enthalpy of formation for C6H12O6. The problem is that you have carbon in the diamond form, and it should be in its graphite form. Graphite is the more stable substance at 25 degrees Celsius and 1 atmosphere of pressure. And once again, if you're not sure of that, take a look in Appendix C. So those are some examples of equations that form standard enthalpies of formation. Now let's take a look at how we can use these tabulated data to find the enthalpy of a particular reaction. Take a look at practice exercise 5.10. Write the equation corresponding to the standard enthalpy of formation of liquid carbon tetrachloride. So we need to take carbon in its standard state, which is graphite, and add it to chlorine, Cl2, in its gaseous state. And we need to make CCl4, which is a liquid at that temperature. And we have to make 1 mole of that, so that means I'm going to have 2 of these right here. So there's the standard enthalpy of formation equation. Secondly, calculate the standard enthalpy change for the combustion of 1 mole of benzene, C6H6, to CO2 and H2O. And for this, I'm going to have to use some standard enthalpies of formation, either in Appendix C or on page 192. And the equation that's used to calculate this now is based on what the reaction is that we're looking at. In this case, it's a combustion of benzene. So C6H6 plus O2. Remember, combustion reactions are when they're combined with oxygen and they burn, and they form carbon dioxide, CO2, and H2O. And we're going to assume that it's the standard enthalpy change, so it's at standard conditions, so I can use the values that are given on the table on page 192. And the equation used to find it for the overall enthalpy of a reaction is said to be the summation, this symbol right here, the sigma symbol means summation, of the enthalpies of the products, enthalpies of formation of the products. So I should put a little F down here and a little circle right up here, minus the summation or the addition of the enthalpies of formation of the reactants. And so what we're looking at actually is the change in enthalpies of formation from products to reactants. And the one thing that I did not put in here for both reactants and products is that you need to multiply the reactants and the products times, I'm going to put the letter N in here, times their coefficient. So N means coefficient in the balanced chemical equation. Coefficient in the balanced chemical equation. So if I take a look at this reaction that I wrote right up here for the combustion of benzene, it would be C6H6 plus, and I'm going to write it so there's 1 mole of C6H6 plus 15 halves O2 yields 6 CO2s plus 3 H2Os. And if I want to find the overall enthalpy of reaction, now what I do is I take my products' enthalpies of formation that I look up on page 193 or in Appendix C, and for carbon dioxide I'd have to multiply it by 6. So 6 times carbon dioxide, which is negative 393.5 kilojoules, plus 3 times water, which is negative 285.8 kilojoules. Those are my products, and notice I summed them together by adding them. And then I'll subtract the products now from the products, I'll subtract the enthalpies of the reactants. And the reactants in this case are benzene, C6H6. Notice it's 1 mole of that. So 1 times benzene, which if I look that up on the Appendix C, or page 193, it's 49 kilojoules. Notice these are all measured in kilojoules. I didn't put the kilojoules in there, but I just know that they're all measured in kilojoules because that's on the table. Plus the enthalpy of formation of 15 halves times oxygen. And if I look up oxygen's enthalpy of formation on the table, it turns out its enthalpy of formation is 0. Hey, that's interesting. Did you know that the enthalpy of formation for any element in its standard condition state is 0? Yeah, it is. Kind of an interesting thing. If you look in Appendix C and spend some time there, you'll find out that everything is 0. Anyway, multiply 6 times this, plus 3 times this, minus 49. Try that on your calculator right now. Pause the video if you need to. And it turns out to be that the overall enthalpy for the reaction is negative 3267 kilojoules, and that's kilojoules per mole of benzene that's burnt. The letter B says, compare the quantity of heat produced by the combustion of 1 gram of propane to that produced by 1 gram of benzene. Now this right here was the number of kilojoules released per mole of benzene. And so what I wanted to know is how many kilojoules are released for every 1 gram of benzene. For every 1 gram of benzene. And if I add up C6H6 on the periodic table, in 1 mole of C6H6, there are 78.1 grams, and that turns out to be negative 41.8 kilojoules per gram. And now I'm going to compare this. to the enthalpy produced by the combustion of 1 gram of propane, and it turns out that the enthalpy of combustion for propane, which is actually something we did in a sample problem, I think, last videocast, the enthalpy of combustion of propane is negative 2220 kilojoules per mole. And this is for C3H8. And if I want to know it per gram, remember I will put grams down here and moles in a position where it's going to cancel. C3H8. And in 1 mole of C3H8, there are 44.1 grams. And if I go ahead and notice that my moles cancel with my moles, I end up finding out this enthalpy is negative 50.3 kilojoules per gram. So notice that per gram, you're going to get just a little bit more energy for propane than you are for benzene. And just as a comment, both propane and benzene are hydrocarbon, and as a rule, the energy obtained from the combustion of a gram of hydrocarbon is between 40 and 50 kilojoules per gram. And that's what it turns out to be. That's kind of a standard rule. Let's take a look at one other example problem. Looking at the next page, it says, using standard enthalpies of formation listed in table 5.3, calculate the enthalpy change for the combustion of 1 mole of ethanol. So here's another sample problem where we have 1 mole of ethanol. 1 mole of ethanol right here, plus 3 oxygens goes to 2 CO2 plus 3 H2O. And to do this, remember to find the enthalpy of the reaction. What I'll do is find the summation of the enthalpies of formation of the products. Don't forget I have to multiply that by some number n, and subtract from that the enthalpy of formation of the reactants. Products minus reactants. And in this case, what I'll have to do is look up my enthalpy for my carbon dioxide and multiply it by 2. Carbon dioxide, remember, was 393.5. Add that to my water, multiplied by 3, which was negative 285.5. Oh, 285.8, I'm sorry. And then that's my products. And subtract from that the reactants. And the reactants in this case were oxygen and oxygen and methanol. Now the oxygen, if you remember, is from its constituent normal, is just an element, and so it'll be 3 times 0 because the enthalpy of formation of oxygen is 0. But the C2H5OH, this is supposed to be a 5 right here. I'm not sure if it's a 5 in yours, but it's supposed to be a 5. Is negative 277.7 kilojoules per mole. And notice there's a 1 in front of there, so I don't need to multiply that by anything. And then if you take these numbers, multiply them, add them, multiply them, add them together, subtract from it the negative 277.7, turns out that we end up with negative 1,367 kilojoules for this reaction. That's a 1 right there. Negative 1,367 kilojoules. Well, there's a couple other sample problems here for solving for other things in these equations. Let's just take a look at this one and set it up. This one says the standard enthalpy for the reaction is 178.1 kilojoules. From the values of the standard enthalpy formation of CaO and CO2 given in 5.3, calculate the standard enthalpy formation of CaO3. So here they're actually putting a twist on the same type of question, where normally the equation is enthalpy of reaction is equal to the enthalpy chain of products minus enthalpy change of reactants. And in this case, they tell you the enthalpy change of the reaction is 178.1 kilojoules, and this is equal to the enthalpy of formation of products. And we can look up the products CaO and CO2 in the table on page 192. CaO is negative 635. And CO2, or carbon dioxide, is negative 393.5. And notice each of those has a coefficient of 1, and that's my products, minus my reactants. And I have only one reactant here, that's CaCO3. And this is the thing that I want to find, the enthalpy of formation at standard conditions of CaCO3. And so since I know the enthalpy change for the whole reaction, and I know these are the standard enthalpies of formation of those two things, this now becomes my variable and my thing to solve for. So it's actually the same type of problem, but now it's having you solve for a different variable. And if you want to take a look, at this one, I believe the problem is completely solved for you on page 195 in your textbook. And they go ahead and solve this little mathematics right here, and they end up with an enthalpy of formation of CaCO3 of negative 129.7 kilojoules. And that's the enthalpy of formation of CaCO3. You can take a look at the work on that page if you'd like to as well. There's one other practice exercise right here using copper and hydrogen, and this one has also worked for you on page 196 of your textbook if you want to look at a further example problem using enthalpies of formation. Good luck with your enthalpy of formation reactions and also calculating the enthalpies of reactions from enthalpies of formation.